Welcome, everyone. I am Joel Armengol, researcher at the Technological Center LEITAC. LEITAC collaborates in the generation of technological knowledge and its application for the development and reinforcement of the competitive capacity of companies in the field of technology, innovation, and sustainability. For the CleanTech course, we have prepared the Unit 3.3, Environmental Impact of Sourcing Fibers Worldwide. And if you are ready, we can start. I will share the slide with you and briefly introduce what we will be talking about today. First, I will discuss the environmental impact of sourcing fibers worldwide, followed by environmental impact of natural fibers, and then environmental impact of man-made fibers. And to finish, the methodologies and tools to measure the environmental impacts. Now, we will move on the first part of the unit, section 3.3.1, concerning the environmental impact of sourcing fibers worldwide. To start, we will give you an introduction to provide you with some more context on the subject. As you saw in module number 2, the textile sector has one of the highest environmental impacts globally, mainly due to its high carbon and water footprint. Textiles is one of the sectors that generates the highest amount of greenhouse gases per unit of material produced. Producing 1 ton of textiles generates 17 tons of CO2 equivalent. This unit will be more specific about what environmental impact different fibers have, and at which point in the production chain they cause the most damage to the environment. I will now introduce the fibers that we will cover in the presentation. First of all, it is important to differentiate between the 2 main groups of textiles, natural fibers and man-made fibers. Natural fibers, as you saw earlier in the module, are any hair-like raw material which can be obtained directly from animals or plants, and which can be made into non-woven fabrics such as felt or paper, or after spinning, into woven fabrics. Man-made fibers are fibers made from natural polymers that exist in nature. The resulting fibers can be chemical modified, but their sources are natural polymers. We will continue by closer examining the following fibers, which are the most commercialized in the world. Regarding natural fibers, we have cotton. Cotton is a soft, fluffy staple fiber that grows in a bowl or protective case around the seeds of the cotton plants of the genus Gospeum in the mallow family Malvaceae. Wool, as you know, is the textile fiber obtained from sheep and other animals. Cellulosic fibers, other than cotton, are fibers made with ethers or esters of cellulose, which can be obtained from the bark, wood, or leaf of plants, or from other plant-based material. And for the other textile group, man-made fibers, we have polyester, which is a group of polymers that consist basically of repeated units of an ester and that can be used for making fibers, and polyamide is a synthetic polymer made by the linkage of an amino group of one molecule and a carboxylic acid group of another, including many synthetic fibers such as nylon. This slide explains the key points on the environmental impact of fibers worldwide. Increases in environmental impact are related with the growth of fast fashion. Fast fashion is characterized by the multinational retail chains. It relies on mass production, low prices, and large volumes of sales. The business model is based on copying styles from high-end fashion shows and delivering them in a short time at cheap prices. Typically, using lower quality materials. To better understand the current situation, we need to look at the period between 1996 and 2012, where the prices of clothing has increased only 3%, whereas general consumer prices rose by about 60%. In the consumption basket of European Union consumers, the contribution of clothing fell by 56%. It is important to remember that the supply chain of textile and fashion industry is long and complex and includes agricultural activities, petrochemical fiber productions, manufacturing, logistics, and retailing. Each production step to obtain a fiber has an environmental impact related to water, material, chemical, and energy use. Here, we will focus on the group of natural fibers and their environmental impacts. Synthetic fibers are commonly seen as bad and natural fibers as good, but this is not always true. When we focus on the production of raw materials, natural fibers have a larger impact on the environment than man-made fibers. Moreover, natural fibers have more impact, especially cotton, in the process of water use: bleaching, dyeing, printing, and finishing. On the other hand, the production of natural fibers tends to use less energy than synthetic fibers. This section highlights the most used natural fibers in the textile sector, as well as their environmental impacts. They are classified in two main groups. Natural plant fibers are the fibers that we can obtain from the following parts of plants. The fibers collected from the seeds of various plants are known as seed fibers, for example, cotton and camel. Fibers collected from the cells of a leaf are known as leaf fibers, for example, banana, pineapple, etc. Bast fibers are collected from the outer cells layers of the plant's stem, for example, hemp and jute. Fibers collected from the fruit of the plant, for example, coconut fiber, and fibers from the stalk of plant, example from wheat, rice, barley, bamboo, and straw. Regarding animal fibers are fiber or wool taken from animals or hairy mammals, example, sheep wool, goat hair, cashmere, mohair, alpaca hair, horsehair, etc. It also includes fibers secreted by glands, often located near the mouth of insects during the preparation of cocoons, example, silkworms. So, cotton is the most used natural fiber for textile and one of the oldest fibers under human cultivation. There are traces of cotton cultivation going back as far as 7,000 years. Conventional grown cotton fibers are often questioned for the intensive use of pesticides and irrigation during the cultivation, and more sustainable options are requested such as organic cotton. Further on, we will see a difference between organic cotton and conventional cotton. 3% of the world's irrigation water use is related to natural fibers, and 95% of which is associated with cotton production. Here, we show the environmental impact associated with 1 kilogram of cotton fiber. As we see before, huge quantities of water are required to obtain 1 kilogram of cotton fibers. More specifically, 1,559 liters of fresh water. The amounts of CO2 emissions are also relevant, estimated at 2.2 kilograms per kilograms of fiber. Furthermore, energy consumption reaches 48 kilowatt hours per kilogram of cotton fiber. It is also important to highlight the large-scale use of pesticides, fertilizers, and other chemicals in cotton cultivation that cause significant additional environmental impacts. The graphic we can see here shows us the annual production volume of plant fibers other than cotton. There is a great variety of plant fibers on the market. Jute is the dominating fiber type, which is almost exclusively cultivated in Bangladesh and India. Core fiber is collected from the coconut plant and is the second most produced natural plant fiber globally. Flax production occurs to a large extent in France and Belgium. When these types of fibers are used as bast fibers, the fibers are extracted from the stem of the plant and subdued to retin. Cellulose fibers are often claimed to be a sustainable alternative to cotton, since the chemical structure is based on cellulose just as in cotton. There are many similarities in the comfort properties. Continuing with the environmental impacts required to obtain 1 kilogram of cellulosic fiber, water requirements are much lower for cellulosic fibers than cotton, with only 92 liters of water per kilogram, which is less than 6% of the cotton water footprint. On the other hand, CO2 emissions are higher than for cotton fibers, with 3.3 kilograms of CO2 per kilogram. Finally, energy consumption for cellulosic fiber production is 92 kilowatts hour per kilogram of fiber, which is almost double that of cotton. Concerning animal fibers, such as wool. Wool is a natural and renewable fiber and could have been considered an environmentally friendly option. Unfortunately, the extensive sheep farming practiced to meet global demands has had disastrous consequences for the environment. Sheep survive through grazing, which can have a positive impact on certain types of ecosystems when it is well managed. But when land is overgrazed, it does not have enough time for vegetation to grow, which can cause the soil to weaken, making it vulnerable to erosion and desertification. Sheep also release methane, a gas that is 25 times worse for global warming than CO2. The environmental impacts to produce wool fibers are also significant. It involves huge quantities of water to raise sheep. More specifically, 1 kilogram of wool fibers production requires 530 liters of fresh water. The amount of CO2 emissions are also relevant, with 17 kilograms of CO2 equivalent emitted per kilogram of wool. Energy consumption associated with the production of wool is about 120 kilowatt hours per kilogram of fiber. Concerning silk, which is also considered an animal fiber. The environmental impact of silk can be attributed to inefficiency in agriculture infrastructure, specifically electricity supply and irrigation. Climate conditioning for silkworm rearing encourages energy consumption. Wastewater is generally discharged to groundwater, acting as a low-level pollutant. Silk fibers are a much more valuable textile material than other natural fibers, with very different mechanical properties. Most of the environmental impact of sericulture is related to cocoon production. Embodied solar energy of mulberry leaves and the wood used during cocoon processing account for the majority of renewable energy demand. Electricity for cocoon, drying, and irrigation are the main sources of non-renewable energy demand. Most of the associated global warming potential is related to fertilization and emissions from composting rearing waste. The majority of ecotoxicity impacts result from pesticide use. As we haven't seen, silk fibers have several handicaps for their production, which is why silk is the fiber that causes proportionally the greatest impact on the environment per kilogram of fiber produced. Specifically, per kilogram of silk, 54,000 liters of fresh water are consumed, 80.9 kilograms of CO2 equivalent emitted, and 516 kilowatt hours of electricity required. Moving on to man-made fibers, Historically, the development of synthetic and regenerative fibers has to a large extent been driven by the high price and uncertainties in the supply chain. Here, the main challenge is to develop a sustainable production path to substitute the 71 million tons yearly produced synthetic fibers that are today fossil-based. Polyester makes up 82% of man-made fibers and dominates the textile market, followed by polyamide or nylon, polypropylene, and acrylics. Further, the microplastics problem is potentially an issue with all synthetic fibers. Environmental impacts concerns are the contamination of groundwater and process emission with high amounts of heavy metals, managed salts, sodium bromide, antimony oxide, and titanium dioxide. Moreover, crude oil conversion into petrochemicals releases hazardous toxins into the atmosphere that impact on humans as well as the environment. Making a simple comparison of the environmental impact between natural fibers and synthetic ones, the latter are not necessarily worse, but it is important to consider other aspects apart water consumption, energy consumption, and CO2 emissions. Other impacts on the environment are related to the time it takes for the fiber to degrade, as synthetic fibers typically remain in the environment for many more years than fibers. In this part of the unit, we will highlight the most used man-made fibers in the textile sector and their environmental impacts. Here, the two principal man-made fibers are investigated further, namely polyester and polyamide. So, concerning man-made fibers, such as polyester. Polyester is a category of polymers that contain the ester functional group in every repeat unit of their main chain. Polyester is a synthetic fiber that is questioned due to its mostly fossil resources origin and the release of microplastics. It is the most widely used fiber in the world, mainly in clothing productions. Another important issue is that polyester is not biodegradable and will persist in the ecosystem even when it eventually breaks apart. So, in order to obtain 1 kilogram of polyester, there are required 21 liters of fresh water. Emissions amount to 3.3 kilograms of CO2 equivalent, and the most impact is related with the energy consumption, with 108 kilowatt hours. Regarding the other man-made fiber, polyamide. Polyamide fibers are also known under the brand name nylon. There are several types of polyamide fibers, with the common denominator being the nitrogen bond. Regarding environmental impacts, the production of polyamide fiber emits nitric oxide, which is a gas is 300 times more potent as a greenhouse gas than CO2 and 15 times more than methane. Polyamide fibers have the same issue as polyester in terms of not being biodegradable or compostable. Furthermore, the consumption of this type of fiber increased the dependence of fossil fuels. What is needed to obtain 1 kilogram of polyamide fiber? It requires 40 liters of fresh water, generates 8.3 kilograms of CO2 equivalent emissions, and 160 kilowatt hours of energy, which is, on all accounts, is significantly more than polyester. Here, we review the key points to consider concerning the life cycle assessment, or LCA, to determine the environmental impacts of fibers. The textile and fashion industry has a long and complex supply chain, starting from agriculture and petrochemical production for fiber production to manufacturing, logistics, and retail. Each production step has an environmental impact due to water, material, chemical, and energy use, but the production of raw materials is responsible for a large share of the environmental impact of the textile sector. Raw materials are in an unprocessed state. they might need to be cleaned, soaked, or treated with certain substance before threads are made. The textile industry uses raw materials from natural and synthetic or man-made sources. The type of raw material used depends on textile being made and the process that a factory uses. Beyond the type of fiber, the method of fiber production is also of a great importance. In order to create a sustainable textile, the main change factors have been linked to eco-materials, so less and harmless waste, reusing, recycling, lesser usage of energy, water, and chemicals, and ethical issues in production processes. The energy source used throughout the production chain also influence the environmental impact. All energy sources have some impact on our environment. Fossil fuels, coal, oil, and natural gas do substantially more harm than renewable energy sources by most measures, including air and water pollution, damage to public health, wildlife, and habitat loss, water use, land use, and global warming emissions. The country of fiber production is important for determining the environmental impacts. In addition, products may be managed in various ways. When they reach their end of life, they may be reused, recycled, used for energy recovery, or disposed of, which will have different impacts on the environment. Here, we will briefly revise the life cycle assessment methodology. As we could see in Module 2, LCA is a useful methodology to determine the environmental impacts of textile fibers. We also saw earlier that cotton is one of the most used fibers in the textile sector. So, it will subsequently be described what steps are necessary to determine its impact on the whole value chain. The stage through which cotton passes from its conditions as a raw material to its transformation into fiber are the following. During harvesting and collection, the seeds are collected from the cotton bush and put into bales for transport to the factory. There, the cotton undergoes a pre-cleaning, whereby the cotton is blown to make it fluffy and to soften its fibers, thus getting rid of any remaining impurities. Subsequently, the cotton is dried and blended in drying machines, since the harvested cotton usually has a moisture content of around 5–6%. Once the cotton is ready, it is fed to the gingham station, where the fiber is separated from the seed. This stage can be carried out with two different technologies, roller or saw ginning machines. The lint obtained is again cleaned and combed, separating the cotton fiber from a byproduct stream of lint. The aim of this post-cleaning of the lint is to further remove possibly impurities in the cotton. In the last stage, the cotton lint is pressed and packed for storage or transport to the textile mills for the further processing into yarn. To recognize the uses and advantages of the LCA methodology, this unit shows a comparative LCA between conventional and organic cotton. Comparative life cycle assessment is a way to determine which product or process is better in terms of environmental impacts. To start, it is necessary to define the impact categories that will be measured. In this case, the focus will be on global warming potential. Climate change is measured as global warming potential. It is deemed to be one of the most pressing environmental issues of our times. The category indicator results are provided in kilograms of CO2 equivalent per functional unit. Eutrophication potential, also known as over-fertilization, was also chosen for its connection to air, soil, and water quality and relevance to agricultural systems. The category indicator results are shown in phosphate equivalent per functional unit. Acidification potential is causing, for example, acid rain, was chosen because it is closely connected to air, soil, and water quality, and relevant to environmental aspects of agricultural systems. The category indicator results are shown in kilograms sulfur dioxide equivalent. Non-renewable primary energy demand is the primary energy demand from non-renewable sources. Example, petroleum, natural gas, etc. Its relevance to energy and resources, efficiency, and its interconnection with the climate change. The category indicator results are shown in megajoule per kilogram. Water use and water consumption. Use of water by human activity. Use includes, but is not limited to, any water withdrawal, water release, or other human activities within the drainage basin impacting water flows and quality. Regarding water consumption, is the water removed from, but not returned to the same drainage basin. Water consumption can be because of evaporation, transpiration, product integration, or release into a different drainage basin or the sea. The category indicator results are shown in cubic meter per kilogram. Regarding system boundaries, the system under consideration is a cradle-to-gate life cycle inventory, including the cultivation of the cotton plant until farm gate, the transport of the seed cotton to the gin and the ginning operations until the fiber is packaged in bales and is ready for shipping. Consequently, this slide shows us the LCA impact results for the different categories, where we can differentiate the impacts caused by conventional cotton versus organic cotton. In summary, the data represent an aggregate average life cycle inventory of global organic cotton fiber production. While data was collected from a number of countries, the study does not compare the impact of organic cotton production between countries or within regions in countries. The results of this study can be applied as a reference value for organic cotton productions worldwide and can be used with confidence in any further LCA studies, example along the value chain of the apparel industry. So, the results indicate that organically grown cotton has the following potential impact savings per 1,000 kilograms of organic cotton fiber relative to conventional cotton. 46% less global warming potential, 70% lower acidification potential, 26% reduced eutrophication, 62% lower non-renewable primary energy demand, and a 91% lower freshwater consumption. To put it simple, organic cotton is a more sustainable solution. Organic cotton uses lower carbon due to less fuel and energy consumption, because it goes through a chemical-free production process. It also prevents water contamination. Organic farming practices avoid using harmful chemicals, while aiming for environmental sustainability and the uses of fewer resources. Chemical-free agriculture land even stays fertile much longer than land hampered by the constant use of pesticides. So, organic cotton farmers generally have a longer cotton commodity lifespan than otherwise. Other important points to take into account related to cotton crops are the following. Organic soil tends to be healthier, which can lead to climate change mitigation and boost the ability to adapt to extreme weather events such as drought and floods. Conventional cotton relies heavily on genetically modified organisms herbicide tolerant for managing pests. However, because GMO are banned in organic production, Organic farmers rely on a healthy ecosystem to manage pests and use soil and biodiversity, building techniques such as crop rotation, resistant and tolerant varieties, and fostering beneficial insects. On the two final slides, you can find the main reference, indicating the sources of information used in the presentation. Thank you very much for your attention.